we will move on to the next tutorial. It's an overview of reference frames and coordinate systems in the SPICE context. And actually it's quite nice because I never thought that my first year of university algebra course would get that far. Right? So this is mostly about that. So yes, so in here we provide an overview of the reference frames and the coordinate systems. Also it has to be, well, you have to remember that this is always in the context of SPICE. You might find divergent definitions in other in literature. Some of the things that we're going to show here, you have already seen, you already saw yesterday in the fundamental concepts, if I'm not mistaken, tutorial. So basically, the details of the frame subsystem can also be found in these other tutorials, in the frames kernel tutorial, using frames, dynamic frames, and the frames required reading. We're also going to go through the dynamic frames, which is not usual for the basic training, but we're going to go through it on Friday actually. And details about the SPICE coordinate systems are found as well in the headers of the functions for the routines that are for coordinate conversion. So one could say that next to time, so which we already went through this morning, the topics of reference frames and coordinate systems present some of the largest challenges when it comes to documenting and understanding observation geometry. And that's mainly because there's differences in definitions, there's a lack of concise definitions, and there's also a bunch of special cases. It's also an issue, the fact that the evolution of the frame system in SPICE has also introduced some divergencies, and then also the substantial frames management capabilities that are available. So the idea of this tutorial is to basically to provide some clarity on this subject always within the SPICE concept. So and again, as I mentioned before, some of the terminology that is used here might not be consistent with things that you can read elsewhere. Okay. So, as we mentioned yesterday, for SPICE, a reference frame or a frame, it's specified by an ordered set of three mutually orthogonal and possibly time-dependent unit length direction vectors. Okay, reference frames will always have an associated center. You might find these defined as a coordinate frame somewhere else, but don't use that in the context of SPICE. Now, when we talk about the coordinate system, we actually specify a mechanism in order to locate points within a reference frame. Okay, and basically, it's very important that when you use state or orientation data, you have to understand both the reference frame that you're using and the coordinate system that you are using to specify your position in that given reference frame. So, going deeper into reference frames, as a convention within SPICE, all reference frames are right-handed. So this means that x cross y is z, right? You just do like this. So we go from x to y, our finger points higher up, and that's z, okay? I've only seen divergences for heliophysics so far. Besides that, I've never found any case in which the contrary was needed. So, a center of a reference frame must be a SPICE ephemeris object, whose location is coincident with the origin of the frame. So, SPICE ephemeris object is any object in SPICE that we can associate an SPK file for, okay, or an SPK segment or whatsoever. So, that said, the center of any inertial frame is always the solar system barycenter, which is, one could say, our absolute origin for SPICE. And the center of a body fixed frame is the center of the body. Again, when we say a body, we actually say an ephemeris object. And we could be, if it's a natural body, that's a sun, it's a sun, planet, satellite, comet, and asteroid. And again, the location of that body center is specified using an SPK file. When we talk about the topocentric body, or a spacecraft, or an instrument frame, that should also be an object that we would specify the position of with an SPK file. Okay. The center of the frame usually does not play a role in the specification of states, because when we do subtraction or addition, the center disappears. But it's used when we do lifetime computations to the center of any non-inertial frame being used. Okay. Now, going into some definitions. An inertial reference frame is a non-rotating reference frame with respect to the stars and with a non-accelerating origin. So velocity might be typically non-zero, but acceleration is negligible or non-existent. So a couple of examples is J2000 or ecliptic J2000. Whereas for a non-inertial frame, that's a frame which is accelerating, and that includes rotation as well. And some examples, the typical ones that we're going to find, are body fixed frames that are associated with a natural body, so that move along the rotation and the translation of a natural body, such as a planet or a satellite. Topocentric frames, which are associated with an object on or near the surface of a natural body. That could be a DSN station, a rover, a landing site, and so on and so forth. Spacecraft, which will have the main structure frame bound with the path of the spacecraft itself. An instrument, so we can associate one or more frames to each instrument, for example, to account for misalignments and so on. And we also have like frames for the spacecraft antenna, solar array, etc. Finally, we've got dynamic frames, which is a special family of frames, and it's unique to SPICE. And these have time-dependent orientation that can be defined in many different ways, which does not include those frames whose orientation is provided by a C-kernel or by a planetary constants kernel. Okay, and again, we will see a tutorial on this on Friday. So for J2000, don't get confused, because J2000 is the name that we usually also use for the zero epoch of the ephemeris time system. Okay, so this frame definition is based on the Earth equator and equinox, and basically what is determined from observation of planetary motions plus other data. So basically what we've got is that on the one side we have the ecliptic plane, and then we have the equatorial plane, which is the plane normal to the Earth spin axis. So the Earth spin axis is used as the z-axis of this frame. Actually, at the epoch 2000 January the 1st, 12th, barycentric dynamic time. And then the intersection between this plane at that epoch and the ecliptic plane will give us what is called the vernal equinox. That's going to be our x-axis, and then y is z cross x, and that completes our orthogonal frame. This frame has a, so to speak, more modern definition, which is the ICRF, the International Celestial Reference Frame, and this is defined by the adopted location of 295 extragalactic radio sources. Okay, now they are not exactly the same, but and actually the difference is a very small rotation of less than 0.1 arc second. But we consider those two frames exactly the same in SPICE. Actually, in reality, what is implemented is ICRF and not the J2000 definition. But for historical and backwards compatibility reasons, we use J2000, and you cannot actually call for ICRF in SPICE, unless you define it yourself. And again, since we make those two definitions equal, there's no transformation required to convert from one to the other. Body fixed frames. So, body fixed frames are tied to a named body, and they actually rotate it. So, the specifications for most common body fixed frames, so the Sun, planets, many satellites, few asteroids and comets, are hard-coded in SPICE. Okay? And those come with this name style IAU underscore the body name. So IAU Mars, IAU Saturn, and so on and so forth. Nevertheless, even though their definitions are hard-coded in the toolkit, you still need to load the PCK file, the latest generic PCK file, which will provide us the required parameters for them, for their orientation to be modeled. You can also look at the frames required reading document for further information on these kind of frames. Now, what I just mentioned here, the rotation state, so the orientation at a given time, is determined using the text PCK, which contains the latest data published by the IAU. There's two special cases, which are the Earth and the Moon, because although those definitions exist, they should not be used, because there's a higher precision PCKs available, which are explained in this Lunar Earth PCK frames kernel tutorial that, if I'm not wrong, we're also going to have on Friday. This said, a note here, you also have to be careful, because maybe using the latest generic PCK file is not the solution that you're looking for, because maybe the data that you are analyzing is referring to an older version of the basically of the spin axis of Jupiter or whatsoever. So be careful with that. So spacecraft and instrument frames. So they are defined for spacecraft and items attached to a spacecraft, again, such as the antennas, solar arrays, platforms, instruments, and moving parts of an instrument. Those frames that are time varying, so those frames that are moving, are usually defined in an FK, and the frame orientation is usually provided by a CK. The ones which are not moving, the ones that we call fixed offset frames, basically are defined in this frames kernel file. So the frames kernel of a given spacecraft is one of the, let's say, one of the main kernels that you will need to load if you want to get any kind of orientation information for that given spacecraft. And usually it's a very well documented and thorough and long frames kernel that allows us to define something like this. Okay? So in this nice and dense slide, what you can see is a representation of the definition of different reference frames for a given spacecraft. So, well, first of all, we have some position vectors that give us some information on the position of the spacecraft. So we've got an SPK file for the spacecraft that will give us the position of the center of the spacecraft with respect to a given target, for respect to a given origin. So in this case could be Mars. We might have the state of TGO with respect to Mars, and that would give us the center of TGO. And then we would have, for example, the position of the gimbal of the Hagen antenna relative to the spacecraft. That typically comes along with structures SPK file. Usually they are named, they contain the name structures in the file name. And then we would have, for example, the center, or the center location of the phase center location of the Hagen antenna relative to this other structure in the same SPK file. Solar array gimbal position, magnetometer position, you name it. But all these kind of positions are usually provided in this structures SPK file. And then on top of that, we would have the frame definitions to obtain orientation information. So, first of all, we would have the spacecraft frame. Typically, this is a CK frame, the orientation of which we get with respect to, for example, J2000 or maybe to Mars, and it would come in the shape of quaternions or Euler angles or any other kind of origin data for this CK file to be generated. And then from that one we would have a set of fixed offset frames, such as the one for the Hagen antenna gimbal, the one for the solar array gimbal, and one for a given camera. And this would have given orientation with respect to the spacecraft frame. Afterwards, we would have CK-based frames for those objects in the spacecraft that are movable, such as the solar array, if it turns, if it rotates along the rotation axis, or the Hagen antenna that might have a given azimuth and elevation angle. So we would implement those with CK-based frames. Okay, topocentric frames. So topocentric frames are located at or in the surface. Typically one axis is normal to reference asteroid, and that again is used for ground stations, landers, rovers, and so on. This graphic is actually illustrating one example of a topocentric frame, but this is not a standard definition, so there could be many other definitions. So in this particular example, we've got the z-axis that is pointing up, so to speak, so anti-gravity or normal to the surface. Then x points north and y points west, but it could be any other way. Dynamic frames. So the idea here is that for a dynamic frame, the orientation changes with time. So there's several ways to define it, and I just referred to this tutorial on Friday. Again, this excludes frames whose orientation changes with time but is determined by a PCK or a CK. And an example could be like, for example, what is depicted here. So this is geocentric solar ecliptic, whose x-axis is defined by the Sun-Earth vector. The y-axis is defined by the component of the Sun's velocity perpendicular to x. Okay, and z would complete our frame. Now, realize that in order to define this reference frame, we will probably need SPK files for the Earth and the Sun for it to be working. Now, eventually, KNIFE will offer a generic dynamic frames kernel, which is not there yet. But typically, at least for ESA missions, there's what we call science frames or operational frames, and a list of dynamic frames are included. So now we go to the coordinate systems. Again, a coordinate system specifies the method that we use to locate a point within a particular reference frame. And in here we have two different examples. We have a Cartesian coordinate system, so x, y, z position, the x-axis, y-axis, and z-axis. Or here we have spherical coordinates, which we give phi, theta, and that's rho for the Greek. Okay. Now this is kind of important, and this connects a little bit with the SPK tutorial that we had before. So usually when we define a position, we usually say, okay, I am with this, like XYZ distance from the center of the reference frame. Although that's true for SPICE as well, it's better not to think it this way when you use SPICE, but it's better to think that you have a reference frame that has a center, which is an ephemeris object, okay, but that when you compute a state, you will use on the one side an observer that will have a position with respect to the center of this reference frame, and a target which have another position with respect to this reference frame, and both are ephemeris objects. And what we care is about this vector, not what would be, you don't really have to care about the fact that this has a position with respect to the center and this other one has another position with respect to the center. So that said, there's many coordinate systems that can be used, right? So in particular in planetary science, there's a bunch of them, and basically as in the same way that there's many different reference frames that can be used. And although some of them have well-accepted standard definitions, others don't. So you really have to pay attention on what coordinate system you're using, and you have to make sure that the definition that you're using is the same that your colleague is using as well. Okay, otherwise you can have a nasty, spend a good amount of time trying to debug what is wrong. So going into the systems themselves, we start with, and pay attention to this because I always find it really confusing and I never learn it by heart. So let's see if I can learn it today as well. I don't think so. Probably tomorrow we'll have forgotten anyway. So we start with the planetocentric coordinate system. Okay. So in this case, for planets and their satellites, the z-axis, okay, that's plus 90 in latitude, okay, 0 being in the xy plane, so plus 90 latitude, points to the north side of the invariable plane. Okay, the invariable plane is the plane whose normal vector is the angular momentum vector of the solar system. Okay, so we've got all the bodies of the solar system, that's up for angular momentum, and that's the normal of this variable plane. So it's important to note that the longitude increases positively eastward from minus 180 to plus 180 degrees. Not 0 to 360, okay? Minus 880 to plus 880. And latitude increases positively northward from minus 90 to plus 90. Fine. Now, dwarf planets, and that includes Pluto as well, and Ceres, Eris, Haumea, and Makemake, or whatever the name is. Although remember that for what concerns the IDs, Pluto was considered a planet. So they spin in the right-hand sense about their positive pole. Okay, so what the IU now calls the positive pole, it's still referred as the North Pole in spice documentation. And this positive pole might point above or below the invariable plane of the solar system. Okay? So basically, distribution by the IAU inverts what had been the direction of the North Pole for Pluto, Charon, and Ida. Okay? So take that into account. Now, some APIs from the toolkit that are used to convert from or to planetocentric coordinate systems are LATREC, REGLAT, DRDLAT, DLATDR, XM, XFM, STA. Jesus. Okay. Planetodetic coordinate system. So easy to get it confused. So in this case, the longitude is the same as for the one in the planetocentric. So positively eastward from minus 180 to plus 180. But in this case, the latitude is tied to a reference ellipsoid. Okay? And basically, for a given point on the reference ellipsoid, the angle measured from the xy plane to the surface, normal at the point of interest. Okay? So, for other points, equals latitude at the nearest point on the reference ellipsoid. So, you can see it here. So we've got a normal, and that normal is not intersecting in the origin of the ellipsoid. And the angle is this one. So that's the difference. See? The angle is actually higher for the same point. Okay. The range is still from 90 to plus 90, minus 90 to plus 90 degrees. And some of the APIs that deal with planetodetic coordinates are GREC, RegGeo, DRDGeo, DGODR, XF, MSTA. The other one that can get us confused, planetographic. Okay, so CDG, centric detic graphic. So in this case, this is a bit different. So for longitude, it's from 0 to 360, and the sub-observer longitude increases with time as seen by a distant fixed observer. Okay, so that's kind of, let's say, easy to imagine somehow. But with the exception of the Earth, Moon, and Sun, in which the planetographic longitude is positive east by default. Okay? Latitude, same, minus 90 to plus 90. And it's the same one as in the planetodetic, not as in the planetocentric. And this is where you can get nasty divergences with literature, okay? So you could imagine that we could mix planetographic in which the latitude, instead of being the same as in the planetodetic, is the same as in the planetocentric. I had already forgotten. Okay, so be careful with that. Some APIs are these ones: PGR reg PGR, DRD PGR, DPG RDR, XFM STA. Now, be careful, because for dwarf planets, asteroids, and comets, there are multiple inconsistent standards, and actually, Naive and myself strongly suggest you to use only planetocentric or planetary coordinates for those objects. Okay. But again, make sure that when you work with colleagues that you are all aligned with the coordinate systems that you use. To a more less planetary science definitions. On the one hand, we have spherical coordinates. So in this case, longitude is from the plus x-axis to the projection of the position vector on the xy plane. Increases in counterclockwise direction. Okay. And you can check at the API header for restrictions on ranges. Colatitude, okay, so it's from 0 to 180, and it's the angle in between the z-axis and the position vector, okay? There's other names for colatitude, such as zenith angle, the inclination angle, and polar angle. And we have a bunch of spherical APIs. SPH reg, reg SPH, DRD, SPH, DSP, HDR, XM, XFM, STA. Okay. And here's an example of azimuth elevation coordinates. Okay. So in this case, azimuth is the angle from the x-axis, the projection of the vector on the xy plane, and in this case, it increases clockwise from 0 to 360. And the elevation is the angle in between the position of the vector and the xy plane from minus 90 to plus 90, and in this example, the up direction. Okay? Actually, as it says here, SPICE does not currently contain API specific to convert between azimuth elevation and other coordinate systems due to the lack of standard definitions for azimuth elevation. Okay. And there's methods to do that anyway. But for example, you know, intuitively for myself, I would have used counterclockwise definition for azimuth, for instance. Okay, so how could we convert in between rectangular to azimuth elevations coordinates? So first of all, we could examples that we go from the rectangular to azimuth elevation. So we could use right ascension and declination as an intermediary step. So first we would convert rectangular to right ascension and declination using this function, okay, where the range is from 0 to 360. And then we could map right ascension declination to whatever is the azimuth elevation convention that one is using, okay? Another option is using latitude longitude as intermediary. In this case, we convert rectangular to latitude longitude using reglat, where the range is from minus 180 to 180, and then we can map this latitude longitude to whatever our azimuth elevation convention is. Okay. There's another tip here that, for example, you could negate latitude to achieve positive elevation being up in a frame having z pointed down. Okay, so don't let your head explode with this. And here's a summary of the coordinate transformation APIs that we can use. This might be one of those charts that, as Chuck suggested yesterday, you could have printed out and next to your computer screen if you're really using this that much. So basically, you've got here also APIs for position and for velocity transformation. Okay, and you've got latitudinal to from rectangular. These are the ones. Right accession and declination to from rectangular. Okay, these are the ones. I challenge you to learn those names by heart. Planetographic to from rectangular. Genetic to from rectangular. Cylindrical that we haven't talked about, to from rectangular. Spherical to from rectangular, and azimuth elevation to from rectangular, and you've got the names there. Okay, and that's everything for this tutorial.